So it's a pleasure to start this morning session with Guillaume Barraquand, who's going to talk about characterizing invariant measures using symmetries of integrable probabilistic models. So it's a pleasure to come from far away to see the guy who was in the office next door at the ENS. So please, Guillaume.
Thank you, Jesper, and thank you, Filippo, for the invitation and for organizing this. So I will try to explain a general method for integrable probabilistic models that depend on inhomogeneity parameters or rapidities or a set of parameters and that are symmetric with respect to permutations of these parameters. In those cases, there is a way to exploit the symmetry in order to characterize, to determine invariant measures, stationary measures of these systems. So I will first explain. This is based on two joint works, one with Pierre Ledoussal that appeared last year, and also some part that is to appear in a few days, and another work with Ivan Corwin from a few months ago. I will first explain what is the motivation, what type of, for which type of system I wanted to compute the invariant measure, and this will be about the Kpz equation, so this is a stochastic PDE. I will tell a little bit of background about it, but we'll not focus on the stochastic PDE aspects, because in order to compute the invariant measures, we will consider an approximation of the Kpz equation, some discrete integrable model, and then most of the talk will be about this. So I will first explain how the method works in the simplest case, which is not related to Kpz equation, and then we will discuss the log gamma polymer, which can be regarded as some approximation of the Kpz equation. And if time permits, I will also explain that this method works in various cases, including something related to non-intersecting polymers. So to start, the motivation was about the Kpz equation. So it's a stochastic PDE that describes the evolution of a function h of time and space. Space is in one dimension. And its evolution is given by the following equation. Here the term psi is a space-time white noise. And there are subtleties in order to define this equation, but I don't want to enter into these details, and we'll focus on the question of finding invariant measures. So first of all, when the noise is white in time, one can see this evolution as a Markov process in time on the space of, say, continuous functions of the variable x. And then the question is, what are the invariant measures? So first of all, there are no invariant measures because the Kpz equation is a priori describes out of equilibrium systems. But by a slight abuse of language, one can see that there is an invariant measure, a stationary measure, in the sense that the spatial increments of the process admit some stationary distributions. So the stationary measure will say that the Kpz admits a stationary measure in the following sense. So if at time 0, h of 0 and x is distributed according to a Brownian motion in x plus some drift mu, so mu here is any parameter, then for all time t, htx, so the increment htx minus ht0 will be again distributed as a Brownian motion with the same drift. And then we say that the Brownian motion is invariant for the Kpz equation. So this is the case where we consider the Kpz equation on R. This fact was anticipated first in the physics literature. I don't know exactly what is the first paper, but it was mentioned at least in a paper of Forster, Nelson, Stefan in 1977, where they studied the Burger's equation. In the mathematics literature, This fact was rigorously proven in a paper of Bertini and Giacomin from 1997. And here already their approach goes through an approximation of the Kpz equation, namely the asymmetric simple exclusion process. So this has been known for a long time. And what I'm interested in this talk is the Kpz equation on R+. So what the invariant measures becomes when we add some boundary conditions. So here, the Kpz equation on R+ will depend on some boundary parameter in R that I denote by U. And I will, so Kpz U will be my Kpz, so maybe I will. So I'll denote Kpz U the Kpz equation with some boundary condition. And the boundary condition is of Neumann type, so we consider the derivative at the boundary x equals 0, and we impose it to be u. So there are, again, solvencies in order to define this, because actually the solution is not differentiable, but one can make sense of it. Actually, in order to make sense of it, one goes through the Kohlhoff transform, so we say that h is the log of z, and z satisfies dtz equal Laplacian z plus z xi, with the same boundary condition as here up to this change of variables. So this reads dxz at x equals 0 equals u times z, and actually we put u minus 1/2. I don't want to insist on the 1/2. It's related to stochastic calculus. So this, I will call this equation the stochastic heat equation with boundary parameter u. So for this equation, I think it has been known for a while, and it can be deduced by the same argument as in Bertini-Giacomin paper, that the Brownian motion with the drift u, this specific u that appears in the boundary, that is the boundary parameter, is invariant for the process. However, we are still in infinite volume on R+, and we don't expect that there is a unique invariant measure. There should be a family of invariant measures. So let me define them. So invariant processes will depend, of course, on the parameter u, and they will depend on an additional parameter v that is taken to be less than 0 and u. And then I define a process h uv of x to be the logarithm. So I will write a formula and then tell you what it means. Exponential of b2 of x plus 1 over omega integral so here b1 and b2 are Brownian motions with drifts minus v and v, respectively. And this omega here is some independent random variable, independent of the Brownian motions, which is distributed according to the gamma distribution with parameter u minus v. Here, u minus v is non-negative, and when the parameter is 0, we assume that, so the inverse gamma distribution, we assume that when u minus v is 0, this weight will be infinite. So the inverse gamma distribution means that 1 over omega is a random variable distributed according to the gamma distribution, or if you prefer, this omega is a positive random variable that is with density with this density. Maybe there is a normalization 1 over gamma u minus v. Okay, so these are the stationary processes, and the theorem Maybe before the theorem, I will make some comment about this process HUV. So it's slightly complicated. It depends on two-bonded motion and some other variable. There are some special cases that are interesting. When U equals V, so this would arrive, for instance, when U is negative and V is negative. So then I said that U minus V appears here. So here, the inverse gamma with parameter 0, I will say that this is plus infinity, so that HUV is just B2. That is a Brownian motion with drift U. And there is another case where U equals minus V, now negative. It can be shown again that HUV of X is distributed according to some Brownian motion plus UX. It's in that case it's not obvious, but one can show this. So as taking particular cases, taking particular values of V, I recover the Brownian motion with drift U. However, for general V, this process is complicated. The law of H is not Gaussian, and it's more complicated. So the result, as you can probably guess, is that for all V less than 0 in U, the process HUV is stationary for the Kpz equation on R plus with boundary parameter U. So that was the main result I wanted to communicate, and then we will see how to prove this using discrete integrable models. Before that, I will make some comments. Yes? Yes, there are Feynman-Katz formulas. So the Feynman-Katz formula would be the same as in R plus, except that there is this boundary condition. So this boundary condition, it can be modeled in two different ways. Either you introduce a line of energy rewards with a certain intensity at 0, or and then the Feynman-Katz formula will be with respect to Brownian motions reflected at 0. Or in your Feynman-Katz formula, you use the heat kernel that has exactly this boundary condition. So that corresponds to the heat kernel of random walks of one motion on R plus with either absorbed or repulsive, well, with elastic boundary conditions. So there are several ways to write a Feynman-Katz formula. Yes. And the critical value will be U equals 0 for the spinning problem. We can make some conjectures. So first we conjecture that HUV for V less than 0 in U constitute all the extremal stationary measures. And all of these stationary measures, we accept that they may arise as large time limit of the Kpz evolution. So it's clear what is the parameter U. This is the boundary parameter, but what is the parameter V? The parameter V is related to the drift at infinity. So we conjecture that for the Kpz equation on R plus, if the initial condition is such that at infinity the drift is given by some real value minus V, then the increment process, so the process HTX minus HT0, converges to, so sometimes HUV, sometimes something else. This depends on some phase diagram. So on the horizontal axis, I put u. On the vertical axis, I put v. And in cases where v is less than u and 0, so in this case, the process will converge to HUV. Oops. In cases where there is a negative drift of the initial condition, the negative drift will disappear at infinity. At infinity, we'll see drift 0, and the increment will converge to HU0. And here, HUU, so this is when u is negative, which means that the boundary is very attractive. And in that case, the invariant process will be HUU, which is a Brownian motion with drift u. So this phase diagram is not proven. This is inspired by a similar phase diagram that was determined by Liggett in 1975 for ASAP on a half-line. However, in that paper of Liggett, so he proves the existence of a certain family of invariant measures and the fact that the process at large time converges to invariant measure with respect to a similar phase diagram. However, there is no description in that paper, no explicit description of the invariant measure such as this. So now, how to prove all this? So, yeah. So this conjecture, can it be made a theorem? So, no, it's not known for, I don't think it's known for full space Kpz. So the full set should be the Brownian motion with drift, with any drift now. And this should also constitute all the extremal stationary measure of Kpz on the full line, but I don't think that this has been rigorously proven. You yeah, it could. Okay, it could disappear in the scaling, but I'm not sure. Actually, it's a good point. So how to prove this result? So as I said, we have a stochastic PDE, but it's a bit difficult to work directly on it. In particular, there is no general method to find invariant measures of nonlinear stochastic PDEs. And it's not very clear even how we would write the generator of such a Markov process. So the approach is to discretize, to approximate the Kpz equation. And there are two main types of models that are used to discretize the Kpz equation. The first type are interacting particle systems. And for instance, we can take the simplest one is the asymmetric simple exclusion process. And the other approach is to use directed polymers. So the approach one could work. Actually, this theorem and the conjecture, so this was first conjectured in a paper joint with Pierre. In this paper, we deduced the process HUV as some limit, a limit as L goes to plus infinity of another process HUVL. And this process HUVL is stationary for the Kpz equation on an interval 0L with boundary conditions. So the same boundary condition at x equals 0 and another boundary condition at x equals L related to the parameter V. So it was possible to have an explicit description of the invariant measure on 0L, then we take the limit L to infinity, and we obtain this process HUV. So this is based on earlier work by Corwin and Knizel. Here, they showed the existence of a stationary process on 0L, and they gave some Laplace transform formula to characterize the distribution, but still the description was not fully explicit. This is based on earlier work by Brick and Veselovsky, which first proved these sort of formulas for the ASAP model, and this is in turn based on representation of the matrix product on that. So in particular, a representation using Askey-Wilson polynomial that is due to Uchiyama, Sasamoto, Wadati from 2004, and that uses the matrix product on that due to Derrida, Evans, Hakim Pasquier. But there are two issues with this approach. First of all, we don't know how to justify rigorously that the large L limit of invariant measures on 0L is invariant for the Kpz equation on R+ with the Kpz equation. Another issue is that these invariant measures here are actually known only with some restrictions on the parameter. There are important restrictions on the parameter U plus V must be positive in order to have workable representation of the matrix product on that. While here in our theorem, we don't have any restriction. So that's why, yes? Yes, so one could first, work out the matrix product on that for ASAP on the half-line. Actually, this has been done. And then, okay, maybe there is a variant of the results of Brick and Veselovsky. Actually, in the paper of Brick and Veselovsky, they discuss it, but the section where they discuss the half-line limit is not so clear that it can be used. And then one would have to also generalize this and go. I will try to convince you that actually the approach using directed polymers is much simpler. So this approach is based on the symmetry argument that I will first explain in a case which is not related to the Kpz equation. So this will be the case related to so-called Shaw processes. So we will look at a model of last passage percolation that was discussed in a talk last week of Patrick Ferrari. So we consider the Z2 lattice. Here I have the point 1, 1, and here maybe NM. And I will be considering upright paths in the lattice, so paths that progress right and up between 1, 1 and NM. And I will define the last passage time. L of NM, it will be the maximum over all paths from 1, 1 to NM of the sum for all points along this path of some energies associated with the vertices. So on each vertex of the lattice, I put some random variable, Gij. Here this is I, and this is J. I will assume that they are all independent. And the last passage percolation time will be to Nm, will be the maximum over path of the sum of the energies along that path. So this quantity here satisfies some obvious recurrence relation. So we have that Lnm equal Gnm plus the maximum of Ln minus 1m Ln m minus 1. And one may be interested in finding invariant measures for this stochastic evolution. So how to do that? I told you that we use symmetry, so we will slightly generalize so here, I haven't told you what is the distribution of the Gijs. They will depend on a family of, on two families of inhomogeneity. So we'll have families of inhomogeneities A1, A2, A3, etc. attached to columns, and B1, B2, B3, etc. attached to rows. And we will assume that Gij follows the geometric distribution with parameter AI, Bj. So here my convention is that if X follows the distribution geometric with parameter Q, then the probability that X equal K is Q to the K, 1 minus Q. So this is the exactly solvable model. Why is it exactly solvable? It is related to show functions. So the main thing we will need is that if we fix n and m, the law of L n plus km jointly for all k is symmetric in the parameter a1, an, and in the parameters b1, bm. So we can permute the AIs, it doesn't change the distribution. We can permute the BIs, it doesn't change the distribution of this whole set of random variables. To show this, so this is a very well-known fact. It comes from the relation between these variables and the Shor process. So first, if we look at L and M, so L and M has the same distribution as lambda 1, where lambda is a random partition, so lambda 1 larger than lambda 2. The lambda i's are non-negative integers, and the random partition lambda is distributed according to, so its distribution is proportional to a product of two Shor functions. So these are Shor functions. And Shor functions are one of the most well-known families of symmetric functions. So they are symmetric in the argument. So this shows that at least in the one-point case, so just L and M, its law is symmetric with respect to permuting the AIs and permuting the BJs. Now one can generalize this. One can use not the Shor measure here, but the Shor process. For instance, if we look at L n plus km and L and M, their joint distribution will be, again, the joint distribution of coordinates of two integer partitions, lambda and mu. And now the probability of these two partitions, lambda and mu, will be proportional to S lambda of B1 to Bm, as the skew Shor function S lambda over mu of A n plus 1, A n plus k, and S mu of A1, an. Again, we see that the distribution is symmetric with respect to the BIs and symmetric with respect to the AIs. One can generalize this result. So here it's just for two last passage time, but one can do that for any number of them and see that the symmetry holds. So this is how one proves this lemma. And this sort of identities in distribution, it can be shown using the Robinson-Chesnut-Knut correspondence. So this is how it was originally obtained in the one-point case by Johansson. It can also be shown using Borodin-Ferrari push block dynamics on this sort of Shor process. There are various ways to prove this. So how this helps to find invariant measures? So the stationary model will be obtained by setting A1 equal B1 equal 1, and say that the AIs will be A for I larger than 2, and the BIs will be fixed value B for I larger than 2. So here, at the point 1, 1, we have a very particular weight that I will denote with a red square. So this weight, its distribution, is geometric of parameter 1. So this is actually plus infinity. And then on the first row and on the first column, we have slightly different distribution. So here we'll have weights with parameter geometric of parameter A, here geometric with parameter B, and in the middle there will be geometric of parameter AB. So what we can do with this, we can use the symmetry. We can permute the lines and permute the columns because the law is symmetric with respect to permutations. So imagine that we are looking at the value of L and M, and the value here of L n plus K M. We will say that the joint distribution of these two last passage time will be the same when we permute. So we will exchange A1 with AN and B1 with BM. When we do that, so we permute some columns, and now here we have N, here we have M. Now our special weight that is infinity will be here, and here we will have geometric random variables with parameter A, geometric with parameter B, and here geometric with parameter AB. But we don't really care about what is above, because so here is the point NM, and here is the point N plus KM. And we are looking at the maximum of a path. So for instance, let's look at Ln plus Km. We are looking at the maximum of path between 1, 1 and here. But here we have an infinity weight. So definitely the optimal path, it will go through here and then here. So this means that Ln plus Km, and this is, if we remove L and M, this will be the same thing as L in the model where I have exchange rows and columns of the passage time from the red square to N plus Km. And this is equal in distribution. So here, the last passage time from the red square to here, this is the same thing as from 1, 1 to here. So this is the same thing as 1 plus K, 1. So maybe minus W11. So here, the conclusion of this is that the law of increments, so a bit as for the Kpz equation, the law of L n plus K m minus L n m jointly in K, it does not depend on nm. So we can look at the process of increments along, say, the horizontal direction, and we can shift it anywhere. It will still have the same distribution. This would be true also for increments along the vertical direction. One can generalize this, but I wanted to show the simplest instance of a stationary measure that one can get from a symmetry argument. So here, what is this process? This process is simply a sum of k independent geometric random variable. So it's a very simple invariant process, and when the stationary measure is uncorrelated, there are much easier way to prove the stationarity. In particular, one can use a local argument. One can say that if at some point in the lattice, here, this increment from here to here is geometric of parameter B, and the increment from here to here is geometric of parameter A, and here we have a weight that is a geometric of parameter AB, one can get convinced that the distribution on this increment of this increment will again be geometric of parameter A and B. So here a local argument would work. But this is only because the invariant process is a sum of IID. It's uncorrelated. In cases where there are correlations in the steady state, this sort of method would fail. And I will show that this symmetry argument, however, works. So to make this argument work in a non-trivial case, I will discuss the log gamma polymer. And we will discuss the log gamma polymer in a half space, which converge to the Kpz equation in a half space. So to define the log gamma polymer, I take inhomogeneities A1, alpha 1, alpha 2, etc. These are positive real number. And I will have a parameter U in R, like for the Kpz equation. This will be my boundary parameter. And so now the model will be defined in a half quadrant. Again, here I have 1, 1. Here I have, say, an M. I will again be considering upright paths that remain in this half quadrant. And now on each vertex of the lattice, I put some variable wij. So here I will tell you directly what is the integrable model. So here we have inhomogeneity parameters that are both attached to rows and columns. The fact that the same parameter appear in both rows and columns is a feature of half-space models. And here for I larger than j, we will assume that this is an inverse gamma distribution with parameter alpha I plus alpha j. And here on the boundary, wii will be distributed as an inverse gamma with parameter u plus alpha I. So this is an integrable model. I need to define the partition function. So the partition function z and m will be, so now it will be the partition function of a directed polymer. So it will really be a sum of a path between 1, 1 to nm of the product for all points along that path of the weights wij. And the partition function solves the recurrence z and m equal w and m plus times z n minus 1m plus z and m minus 1. So this is for n larger than m. And z and n equals w and n times z and n minus 1. And this is a discretization of the stochastic heat equation with parameter u. It's possible to show that these partition functions, they converge to the solution of the stochastic heat equation with boundary parameter u. And the model is integrable in the sense that z and m has the same distribution as some random variable x1, where the vector x equal x1 up to xm has density. So it's a positive temperature version of the Shaw measure. It has a density which is given by some Whittaker function times a function of the other parameters. So here I don't want to explicitly say what is this function f. It doesn't matter. What matters is that these Whittaker functions, or some family of symmetric functions, they are symmetric in the alpha i's. They can be seen as a positive temperature version of the Shaw functions, and they actually converge to some continuous variant of the Shaw function in some limit. I will not say exactly what they are. All that matters is that they are symmetric, and one can also find multi-point generalization of this result. to show the symmetry property that we need. So in the case n equal m, this is due to work by O'Connell, Sepalainen, and Zigouras. And then for the case n larger than m, and for the multipoint case, we have extended this with Alexei Borodin and Ivan Cohen. And one can show that the law of z m plus k m for all k larger than 0 is symmetric in alpha 1 up to alpha m. And now we can use the symmetry argument. So for the stationary model, we set alpha 1 equal, so now it will depend on u and v. So alpha 1 will be v, alpha 2 will be minus v, the other alpha i's will be fixed alpha. And so now we have our half quadrant. So here there is some weight we don't really care about. Here in position 1, 2, alpha 1 plus alpha 2 is equal to 0. So in position 1, 2, we have something weird. We have an inverse gamma with parameter 0, and I say that this is plus infinity. So here we have a plus infinity weight. Here we have a weight which is inverse gamma with parameter so this is inverse gamma with parameter u minus v. This is the same omega that appeared in the description of Kpz invariant measure. What? Oh, you cannot see the blue. So this, can you see it? So this is the weight omega, which is inverse gamma with parameter u minus v. Here on the first two rows, we have inverse gamma with parameter alpha minus u, alpha plus v, alpha minus v, so some slightly different weights. And here all the weights have parameter 2 alpha. And now we are interested in the law, say, at mm and at m plus km. We use the symmetry. So we exchange alpha 1 and alpha 2 with alpha m minus 1 and alpha m. And we get a different picture. So here we have rho m, here we have rho m minus 1. Here we have our infinite weight. Here we have the weight omega. And here we have some process. And what matters is that now when we are looking at the partition function from 1, 1 to m plus km, because of this infinite weight, in the partition function, only the paths that go through here will matter. The contribution of all others will be negligible. And this allows to show that so when we look at the ratio, this will be the same as the ratio from the red square to these points, and the ratio of partition from the red square to the points, so we can forget everything that is below the two spatial lines, and this has the same distribution as z 2 plus k2 over z22. And this is a process that is very explicit. It just depends on two rows of inverse gamma variables. So this, let me call it zuv of k. We can write this zuv of k as some R2 of k. So this is a discrete variant of the exponential of a Brownian motion plus 1 over the omega weight, sum L equal 1 to k of R1 of L, R2 of k over R2 of L minus 1. So here, R1 and R2 are multiplicative random walks with weights that are inverse gamma with parameter alpha plus or minus v. The W is inverse gamma with parameter u minus v. So this, when as alpha goes to infinity, z uv of alpha x, this goes to the exponential of a Brownian motion plus 1 over omega, the integral of exponential b1 of y plus b2 of x minus b2 of y. So this is exactly the exponential of the parameter huv of x that I had introduced in the beginning of the talk. So this is now, so setting alpha goes to infinity, z and m goes to the Kpz equation, and the invariant process converges to HUV. So this is how we prove rigorously that HUV is invariant for the Kpz equation on R+. I think I am over time, so there is another application to non-interesting directed polymers. Instead of considering just one polymer, for which, so the stochastic heat equation is the partition function of a continuous polymer, and then we see that the Brownian motion is invariant. One could consider non-interesting polymers, and then there is still an invariant measure that is some functional of as many Brownian motion as non-interesting polymers there are. So we have a paper to appear soon with Pierre Ledoucelle about this, and the same method of permuting inhomogeneity parameters in the log gamma model work there. I think I will stop here.
Thank you very much, Guillaume, for this cornucopia of nice results. So surely there must be a number of questions. Please.
I want to ask, so if you look for large finite time, you probably see transition from first part of your H which fills the boundary and the other part which doesn't fill the boundary.
You mean that I discussed hxt minus h0t.
Yeah, so
and I say that this is
for large t,
yeah.
say in a model which discrete model, say, for large time, the x part which is very far away from the boundary would not fill boundary, right?
Yeah.
So you probably have transition from this invariant measure which you see as a limit, which is moving boundary. Do you know how this happens?
No, so when we are in infinite volume and we say that we have a convergence, it's the restriction of the process to a compact that converges to the restriction to a compact of something. What we can say, however, is that we can look at hxt for its own sake. And this has a transition. So it depends on the strength of the, you can vary both x and the boundary parameter.
Yes.
So
no, boundary parameter is fixed.
Okay, boundary parameter is fixed.
X is order t, say.
Yes.
Then you don't fill the boundary.
Yeah,
so where it happens?
There should be a transition between a Gaussian behavior and some distribution related to random matrix theory, the scale of fluctuation change. It has not been proved for the Kpz equation or the log gamma polymer model. It has been proved for zero temperature models. It can be proved for slightly different observables. For if you look, if you look at the flat initial data, then one can prove such a statement. In that case, what we see is the BBP transition from random matrices.
So probably there's an interesting thing on this transition from one behavior to another behavior on a moving boundary when X is moving with T.
Yeah, no, I agree that this transition is interesting and it has been studied, but I don't think that it's related to the determination of invariant measures. So the invariant measures, they would arise quite locally
Sure.
in the evolution of the system.
But that's exactly how locally. What is it? It's a power of t, or it's a constant time t?
Ah, okay. So it should arrive at least. So the prediction is that it should arise at well, t to the 2/3 or t to the 1/2, depending on when we are.
I'm not sure. Okay, thank you.
A bit vague question, but how much do you use the fact that this model is integrable in your arguments?
So we only use the symmetry with
Right.
respect to parameters.
So do you think there's a possibility to apply your arguments to some model which is not integrable?
Well, it depends what one calls integrable, but
Quantum integrability?
sorry? No, so for arbitrary distribution of disorder, the law is not symmetric. Clearly.
Right, right.
So
Don't know.
the symmetry with respect to homogeneities is absolutely non-trivial, and it works for very particular weight distributions.
For the full space, for showing stationarity, one uses the Burke property, right?
Yes,
it sounds a little bit similar.
So
no?
the Burke's property, it eventually boils down to a very local argument, the local argument that I've described. If increments vertically and horizontally are a certain distribution, and we add some random weight with the right distribution, then this progresses. So this works well for steady states that are decorrelated, but with correlations, I don't think that there are, one can generalize the arguments that work in full space, and this is why we have used this method.
Okay, thank you.
Are there more questions? Oh, second question.
Is it known something about invariant if you don't have boundary condition, but you have two different slopes on one infinity and another infinity for initial condition? So, right? I mean, so it's not one parameter.
I don't know. But again, it depends on which slope.
No, just two constant. One initial condition,
No,
one infinity is one constant.
I understand. You start with some initial condition which has a drift V1 on plus or a drift V2 on or minus, but then you're looking at large time. But in which direction? Around x equals 0 or around x equals constant
0.
t? Depending on that constant, you would see a different slope. The slope is essentially determined by whatever is the hydrodynamics of the model. So you look at what will be the density in the hydrodynamics that corresponds to the slope you're looking at. Sorry?
I want to look what's happening near the origin at large times. What will be the distribution of the increments of function h?
This is what I'm saying.
Is it known what is the answer?
But it depends where one looks in the rarefaction fan.
Okay, so an announcement or a question maybe?
No, just a small comment. This trick of using symmetry and putting one way to infinity strongly reminds me of the technique for Iserdin-Korepin to determine partition function in the 6-vertex model. There you put one way to 0, but it's essentially the same, right? But actually, in my opinion, it is exactly the same trick. What do you think?
So in the Iserdin-Korepin model, and this is a general technique in vertex models, you want to have a recursion for partition function, and so you will specialize two parameters in a certain way, so that the configuration, part of the configuration freezes, and you're left with a smaller configuration. And so this is the idea behind Iserdin-Korepin. So it's true that it's a bit similar. So here it's not really a freezing, but we have a constraint. The path must go through a vertex. So I agree that the idea is similar. And actually, this method, I believe, can be also used for the stochastic 6-vertex model. So this is something that is in progress that we have looked at with Amol Agarwal, who is here, and Ivan Corwin. Although in the stochastic 6-vertex model, to find invariant measures, we don't really have a freezing of a configuration. But I agree that the method is similar.
In some sense, you freeze the last part of the project.
Yes. Here it's a freezing, yes.
Okay, I think we should thank Guillaume again.